On va reprendre la série de conférences invitées avec le professeur Marc Shapiro qui va nous parler de Life Without Consensus. Donc c'est un peu dans la continuité de la conférence d'avant. Ça sera probablement un peu plus orienté pratique, système distribué. Et Marc Shapiro vient de Sorbonne Université. Donc ceux qui ne connaissent pas Sorbonne Université, c'est par ici sous Jussieu.
Merci Rachid. Donc j'aurais pu faire mon exposé en français, mais on m'a dit de faire comme tout le monde et de le faire en anglais. Donc je sais ce que je vais faire, mais par contre s'il y a des questions en français, il n'y a pas de questions. So I will tell you about...
So what did you say before?
I will tell you about consensus, but especially about not using consensus. And living on the edge, we want to be safe. And but we want to live on the edge is, not quite safe. So this is joint work with my co-authors Annette, Nuno, Chris, and Walter. And this is a accumulation of work that we've been doing in several European projects over the years. So you've all heard about the cloud. The cloud, you have data centers, geo-distributed data centers around the world, doing some they have some storage, they have some computation capability, and they do, they're implementing some application, whatever application you're interested in, social network, gaming, whatever. And the reason you have multiple data centers is so that the clients here can talk to the closest data center, because the latencies, the time it takes for a message to go over the Atlantic is long, right? It takes 50 to 100, a tenth of a second basically, to get an answer over the Atlantic. It takes half a minute to get an answer from Europe to Australia. So you need to have computation facilities that are close to you. And of course, the application here is running at the data center. And you have the whole point of this application is to share some data. So you're in a social network, you are sharing the network, the graph of friendships. If you are in a game, you are sharing the game universe, etc. So to get good latency, you want to talk to the closest data center. But of course, this means that reads are very fast, because you can get, you just do a few milliseconds here, or tens of milliseconds, but writes are difficult. Right? As soon as you have to write something, you may write it to your own local copy of the database, but then you have to propagate. And it looks like every time you do a write, you would have to ask permission from all the other replicas in order to ensure consistency. So there's a well-known theoretical result called the CAP theorem, that says that in a system like this, where the network is slow and can even partition, you cannot have at the same time strong consistency and availability. That is, strong consistency is all the processes in the system see the same states in the same order at the same time. Okay, so this is called strict serializability. But to do that, as I said, every write here has to ask for permission to all the other replicas, and that's necessarily slow. And if the network is down, nothing happens. Your system is not available. If you want availability, that means you have to have the capability to do your writes at one replica without asking for permission, so asynchronously. Right? So you do your write at one replica, and you propagate, and you hope for the best. Right? So that's the available approach. So this is the situation in the cloud, and there are databases out there that provide strong consistency, but they suffer these long latencies. So basically, you cannot commit a transaction in less than, say, 100 milliseconds. That's and of course this is based on consensus. So that was the situation, say, 10 years ago, or 5 years ago. Situation today is very much moving towards what people call the fog. That is, you still have your data centers but they're supplemented by gateways, which also have storage and computing capabilities. And now the clients are going to talk to the closest gateway rather than to the closest data center. So these gateways are called points of presence, or in the future there will be 5G towers with these gateways in them. So there's quite a lot of these resources. But you can see that, so your reads are even faster than before, but you can see that your updates are even more of a problem than before. And the conflict between consistency and availability is harder and harder. But actually, the real world is more like this, right? You have lots and lots and lots of devices, which all have their own storage and computation capability. And they all have some bit of the application logic on the device, right? And they also have, of course, some storage of the application on the device. So here your consistency problem is really hard, right? And I think you just need to look at this picture to realize that you're not going to be able to use consensus. Or at least, if you do, you have to use it very, very, very sparingly. This is not a made-up situation. So a lot of you maybe play games. So here's a well-known game, which is called Pokemon Go. It's a augmented reality game. So you have people walking around, in reality. So here we have Rachid and Maria walking in the Jardin du Luxembourg, right? With their each one with their phone, and the game proposes augmented reality, so they're characters that appear in the geography locally. So Rachid and Maria are standing right next to each other, or talking to each other, and each of them is interacting with the game through the phone. And these characters, are proposed by the system. Vulpix and Pikachu. And the users can interact with the virtual characters, right? So Rachid can say, "Oh, I want to adopt Vulpix as my pet." Yeah, he takes him. And of course, in the real world, you cannot two people cannot have the same object in their hands at the same time. Maria will also say, "Oh, I want to Pikachu as my pet." But the thing is that all this is happening locally in the phone, right? There's very little interaction with the central storage and the centralized game logic in the cloud. So, and this communication here, which exists, is very slow and infrequent. So by the time Maria says she's going to adopt Pikachu as her pet, she can also say the same thing, right? So now we end up with basically two copies of the same thing, right? And this would never happen in the real world. This is an anomaly. This is something, of course, you could do consensus to avoid this, but again, that would be extremely expensive. People just, accept this anomaly and live with it. But there are some applications for which this kind of anomaly is absolutely, not acceptable. So I'll try to go more deeply into these anomalies and the relation with consistency and consensus. I don't know enough about Pokemon Go to tell you a little bit more about it, so I will use another application which I am more familiar with, which is called FMK, which is the application, it is the Danish social security network, the Danish healthcare network. And there's many things to say about this, but let's focus on what is the most important object in this network, which is the prescription, right? So this is the most of the activity of this network. 99% of the activity of this network is about prescriptions. So doctors can create prescriptions, can fill prescription, can populate the prescription with medication, and a prescription has attributes such as the name of the doctor who who created it, the hospital, the name of the patient, the pharmacy, where the prescription should be fulfilled, etc. And so you have operations to create, to populate, to read, and you have an operation that will be used at the pharmacy to process the prescription, that is, to deliver the medication. Okay? And so all this is stored in a database. You have these prescription objects. You have doctor objects, patient objects, pharmacy objects, and of course, all these things are linked. The doctor has a link to all his prescriptions. The patient has a link to all his prescriptions, etc. So you can picture very easily how you would program this in a centralized system. It's not, and you can picture how to do it right. Okay. And one of the things that happens here is, for instance, when you process a prescription, when a pharmacy processes a prescription, let's say this Bob is allowed 2 boxes of this particular medicine, Cositin, but he only asked for 1. But the pharmacy is going to check: do you have are you allowed? Am I allowed to give you this medication? Yes, you're allowed 2. You only asked for 1. Therefore, now you have 1 left. Okay, pretty easy, pretty simple. How to do this correctly is formalized by what's called invariance. So an invariant is a statement about the data. And the statement about the data is going to say, well, you never deliver more than 2 boxes. And if there's a pointer from the doctor to the prescription, then that prescription exists. Okay, so this is called referential integrity. There's another invariant that would say, well, if there's a pointer from the doctor to the prescription, then there must also be a pointer from the patient and from the pharmacy, and vice versa. And that's called an all or nothing invariant, right? And then there's a final invariant that says, never deliver more than these 2 boxes, right? There are probably other kinds of invariants, but I claim, without proof, that these 3 kinds of invariants are sort of universal, and the other kinds of invariants that we care about are combinations of these. So how do we make sure this application is correct? How do we ensure these invariants? In a sequential system, it's very simple, right? You just make sure that every operation individually maintains the invariance, right? And since it's sequential, since every operation individually maintains the invariance, I start here, invariant is true. I do one operation, invariant is still true. Another operation, invariant is still true, etc. It's easy to prove that the invariant will always be true, okay? So if each individual operation is correct in isolation, then the system is correct in isolation. End of story. You can go home and you're happy that your application is correct. In a distributed system, you might say, well, let's use a distributed database. Now, initially I had a centralized database. Now I have a distributed database with replicas all over the country and some kind of very strong connection between them that maintains strict serializability. So in this case, all the replicas see all the operations in the same order at the same time. So basically, it's exactly the same as the sequential system, okay? This is extremely comfortable. This is the comfort zone for application developers, and that's why people love strict serializability, right? But strict serializability, again, requires consensus and will be extremely slow in a very large system and prone to non-availability. So, for instance, how would you maintain referential integrity? Well, you just make sure that so you have the operation of creating a. Remember, you have this create prescription, then populate prescription, and then there's an operation to make it available to the patient, etc. Right? You just make sure. If you in a sequential system or in a strict serializable system, if you just make sure to do things in the right order, first you create, then you populate, and then you set the pointer, you're sure that everything is fine, right? And this is going to remain true in this strictly serializable system. Same thing for the all or nothing. You just make sure that in a single operation, you do the 3 database writes, right? And for the not over deliver, same thing. You have a single operation that is first going to test the what's remaining, this precondition, and if the test is okay, it will do the update. Okay. So we're fine. Unfortunately, as I said, it's not available, so it doesn't work well at scale. And I will claim that it's overkill. You actually don't need this strict serializability for many of these invariants, and I will explain why I say that. So let's say we don't want strict serializability. Let's look at the opposite end of the spectrum, what's called eventual consistency. So eventual consistency is really the complete opposite of strict serializability. Eventual consistency says there's a connection between your database instances, but it's a very weak connection. It doesn't provide many guarantees. The only thing it guarantees is that if you do an update here, I will eventually propagate it to all the other replicas, right? So it's pretty. This is the comfort zone for implementers, right? Strict serializability was the comfort zone for application developers. This is the comfort zone for implementers, right? They have really nothing to do. They just have to send messages and hope for the best. Right? And then anything else, it's all the responsibility of the application developer. Well, what could go wrong? Lots of things could go wrong, right? So, like, I could do my referential integrity. I would, write, first create the prescription and then set the pointer. But the message with the prescription, with the pointer, could go very fast, right? Whereas the message with the create prescription could go, through some weird path and be very slow, and you could get to the pharmacy and say, here, I have a prescription, and the pharmacy would say, no, there's nothing in the database. Right? So that's an anomaly that you don't want. Same thing for the all or nothing. The network could very well send 3 different messages, and they would arrive in any order, and you would not have this property. And worse still, for the don't over-deliver, right? The pharmacy over here might be looking at a completely obsolete version of the database and say, here's your medication, even though you're not allowed, right? So, eventual consistency is broken. We don't want it. But what can we do, right? So, as I said, so the initial assumption was we know how to do a correct application in the sequential case, right? If we assume that each operation individually is correct, then the combination is correct. I would like to keep that property. Okay, strict serializability gives that to me. Gives that to me out of the box, right? And eventual consistency, but it's not available. And eventual consistency gives me nothing, but it's available. Okay, so obviously I need something in between. And I will call this just right consistency. So the idea is you want to tailor the consistency not to some predefined notion of what is a consistency model, but to the application's invariance. Okay? So you want to work your way from the invariance to the protocol. Basically, you want to be as available as possible. As long as you cannot prove that you need synchronization, then you use an available system, an available protocol. But if you show that the requirements of the application impose some kind of synchronization, well, you have no choice. You put it in there, right? Because that's the requirements of the application. And of course, you don't want to do this by trial and error. You don't want to do this on an ad hoc way. You want to have some kind of principled approach for doing this. I will show that for each of the 3 kinds of invariance, there's actually a programming pattern. And what you want to do is to maintain that programming pattern in the distributed system. I'm slow. I have to speed up. So one of the basic building blocks of this is what's called conflict-free replicated data types. So the motivation here is that the standard data model is to have memory cells that you read and write. And reading and writing are not commutative, and therefore that's why eventual consistency gets things wrong, because it reorders things, and therefore you will not get things in the... If you get your updates in the wrong order, you will see things that might diverge or might be even completely wrong. So commutative conflict-free replicated data type says, let's replace assignment by some commutative operation. So here's the simplest example I can think of is a counter. So let's say the counter of medication in your prescription. The doctor adds 1 to this counter, and this operation is replicated at another replica. There's a message sent to this other replica that contains the command add 1. Okay? It doesn't say value equals 1. It says add 1 to your value. Okay? And concurrently, you might have another, maybe the nurse is also adding some medication, so she's saying add 2. And it doesn't matter that the add 2 arrives before the add 1 or the other way around, because these two operations commute. In the end, it's going to be 3. Okay, so that's what you want. So for counters, it's really easy, but you can also do the same kind of trick with other kinds of data types. So this here is is a counter, but you can do the same things with registers. That is, data memory cells that you know nothing about, but you have a little bit of meta information. You can do this with sets. So you have a set, and you can add and remove elements. You can do this with sequences. So sequence, you can think of like when you're doing shared editing. Your text is a sequence of characters, and you can do inserting and removing characters. And these data types, if they're well designed, are plug-in replacements for the sequential data type. So they do everything that a sequential data type does in a sequential execution. So if your sequential program is correct, they remain correct in the sequential execution. But in addition, they have semantics for merging concurrent updates. I don't have time to explain, but oops, why does it come twice? Okay, now let's get to the invariants. So remember, create is supposed to first create the prescription and then set the pointer. Okay? And the fact that there's an order between these two things is really important. Okay? There's an ordering, but this ordering in time reflects an ordering, a partial order of your data between these data items. So in this particular case, the ordering is implication, right? The fact that there is a pointer implies that the fact that there is a record in the database. Right. So in this case, we have this implication here, and the way so this implication, and in general, the way you make sure an implication is true is first you make the right-hand side true, and then you make the left-hand side true. Right. So here we have one replica making the right-hand side true, sending this message to other replicas, and then we have the second. So basically, we've created the prescription on one replica, and now we're populating it on another replica. Right. It's very important that this message arrives before this one, even though they come from different sources. So this is called causal consistency. It's a well-known property of way of implementing protocols in a distributed system. I won't explain how it happens, but it's extremely well known. It's very there's nothing there's no rocket science here. The main the main thing to remember here is that causal consistency is available under partition. The fact that I deliver that this guy will deliver this message before this one is a purely local decision. He doesn't have to ask for permission to anybody. Okay, so it's available under partition, and that's really good, of course. So we have this pattern. this programming pattern where I do something and then I do something else, well, the database, if you want to maintain the corresponding invariance, the database should do the same thing, should propagate things in the right order. Second kind of invariant was what I would call equivalent items. So remember, I want either all these pointers to exist or none. Right? So there's an equivalence relation. Yep. You need to make sure that the database sends them all together. I will skip the slides that explain how this works. I'll just call this bundles and move on. But the important thing here, again, is to remember that this protocol is available under partition. You do not need consensus to implement it. Finally, you have the third one, which is make sure that this variable here of remaining boxes never becomes negative. Okay, that's your invariant, x greater or equal to 0, right? And the way you do that, remember, is that first you do a test, and if the test is true, then you do some kind of modification. So here's the invariant. The invariant is that the remaining number of medications is positive, and if this invariant is true, and to maintain this invariant, so it has to be true at the beginning and at the end of the operation, to make sure it's true, I have a precondition that says check this and then do that. Okay? So here's the problem. Remember that the reads happen at one replica and the writes are propagated to other replicas, and this takes time. So there might be other things happening in the middle. So even though I check my precondition locally, I see that there is medication left on my pharmacy site, there might be another pharmacy site that at the same time has also given away the medications. Right? So there might be, this precondition might be negated by some concurrent operation. We say that this precondition is not stable. Right? But that's in this case, you need some kind of synchronization. But other operations leave the precondition stable. Right? If I was to increase, if the doctor says, okay, now you can have 10 more boxes, that's never going to violate this precondition. And therefore, it is safe to have that operation. So the decrease operations cannot be concurrent, but increase and decrease operations can be concurrent. Of course, increase operations can be concurrent with each other. Okay? So you don't always need synchronization. Right? So if you see that the precondition of one operation is stable with respect to another operation and vice versa, then you don't need any synchronization. Okay? And you're available under partition. If you do, then you have a choice. This is the application designer has a choice. He can choose to weaken the invariant, and that's actually what the designers of FMK did. They said, okay, it's not that important. We will let users cheat and get more medications than in this very rare case where they're able to go to 2 pharmacies at the same time. Or if you say, no, this is really a very important invariant, I will not allow this to be violated, you have only one choice, which is to synchronize. And of course, you will be consistent, but you will not be available. It may happen that you go to a pharmacy, the network connection to that pharmacy is down, and they will say, no, I cannot give you your medication. So my conclusion here, summarize, just right consistency. The idea is to tailor consistency to application invariants. I don't have time to explain, but we actually don't need to know precisely what the invariants are because we can just detect the patterns in the program. And there are many cases, so ordered updates and joint updates, they can be maintained in they do not need consensus, and they can be maintained in an available way. And even for those like precondition modify where you might need consensus, you don't always need it. And you can tell by just looking at the program, by doing some kind of static analysis, you can tell exactly when and you do need consensus and when you don't need it. And I will finish with a plug for our database, Antidote database, which is an open source database which implements all this stuff. Voilà. I have time for questions.